Basic background cosmology, you know, I am sure everybody knows all those stuff, but just to sort of put all the things back and the right notation so that then later on Robbie can use it. So I just going through quickly, very quickly, the basic background cosmology and the things that we use and some of the distance measure that Robbie was talking about, that co-moving distance, the luminosity distance, and the angular diameter distance that Robbie will use later. So those sort of things, I just go quickly, okay? And if you have any question and doubt, you can ask me. And so let's do it. Okay, so as Robbie already discussed in his slides, that when you study cosmology at the background level, we assume that the universe is spatially homogeneous and isotropic. And this is basically spatially homogeneous and isotropic. So one good observational evidence for isotropy is the CMB. So as you look at the CMB, so it is a very isotropic at all direction except this 10 to the power minus 5 small deviation that we have. And then if you, this Copernican principle says that there is not any special point in the universe. All the points in the universe are roughly the same. They are all equivalent. So if you assume that every point on the universe and you assume isotropy at every point of the universe, then geometry says that the isotropy at every point in space is basically homogeneous, fine. So that's the thing that we assume, that the universe is homogeneous and isotropic at large cosmological scale. Obviously, it is not homogeneous and isotropic at small scale because we see galaxies, if you see stars and cluster of galaxies, then there are a lot of huge empty spaces in between. But if you go to very large scale, let's say 100 megaparsec may be a good scale, and then we take a 100 megaparsec box and we calculate defined statistical properties of 100 megaparsec this box, and we take this box as defined place in the universe, we'll get the same statistical behavior of this thing, fine. So that's the thing that we say that the universe is homogeneous and isotropic. So, and as you all know that the cosmology, the basic underlying theory that governs cosmology is the general relativity. And in general relativity, to discuss or to state the geometry, we have to state the distance between the two space-time events. And that distance, in assuming that the universe is homogeneous and isotropic, and universe is expanding, so that is given by what is known as the effort W universe. Okay, Friedman, Robertson, Walker universe. And then in this universe, the distance between two space-time events is given by a simple metric, which is okay, so I believe all of you know this metric. Just to say that if you take out this part, okay, this a squared t part, this is just a flat Minkowski space written in the spherical polar coordinates. And then we add this term k, okay, so this can be positive, this can be negative, or this can be 0, depending upon the Robbie was talking about, the flat k equal to 0. For k less than 0, it is open universe, like an hyperboloid. And k greater than 0 is a sphere or a spherical universe, fine. So we usually what we can do is that we can just take this k, which can be positive, negative, or 0, we can divide it by its magnitude, and then we scale r and all those things in such a way that everything just comes as a squared t. Then k is basically just can be a 0, +1, or -1, fine. So this k is 0, which is especially flat, and k +1 is sphere, and k -1 is an hyperbola, okay. So these are the three geometries we talk about. A square t is the scale factor. Remember, this metric is written in a coordinate which we call the co-moving coordinate, so that if the observer which is at rest, so dr and d theta, d phi, they don't change, then you know this d square, this is the proper time, c is 1 in my this coordinate system, so in my convention. So then this dc square, which is the proper time, which is the coordinate time. So this time is actually a proper time for a co-moving observer, which is actually observer which is moving with the expansion of the universe. So it is actually in that sense a rest at the expansion of the universe. Okay. So then this scale factor, this a square t, is just how any length scale scales. So just means everybody knows that if you take a box and then you take a square and this a coordinate grid. So what happens is this kind of thing is that if this is a scale, okay, then after some time, what happens is that all these galaxies or all these point particles, they are fixed at the grid. Only that grid size is now increased. Okay, so this, let's say at a equal to t1, at t2, this is a equal to t1. So what is happening is that all these galaxies or whatever they are, you just put a grid, they are fixed at the grid. Only thing, so the coordinates are the same, but only thing is that thing that you measure as a coordinate, the scale, that has been increased. Fine. So in that sense, your physical distance is basically your scale factor into your co-moving distance. The co-moving distance are that whatever the coordinate that you choose, the co-moving coordinates, and your physical distance is just the scale factor into this co-moving distance. So if you know, if you can solve this A for different cosmology, we can actually calculate the distance for different cosmology. So that is the meaning of the scale factor, and it actually says that with the expansion, or if this A, as the Hubble's law said, that Hubble discovered, the universe is expanding. So A as a function of time. So any physical length scale, they actually stretched by the scale factor due to the expansion of the universe, so as the any wavelength. So if you have a wavelength, you have, so this is also proportional to the scale factor. So if the light is coming, so they are getting stretched by the scale factor, and that gives you this property of the redshift, okay, because due to the stretching of the wavelength, due to the expansion of the universe, the lights that are coming from faraway sources, they get redshifted, fine. And you can calculate that the observed lambda by the emitted lambda by the emitted lambda, which we call the redshift, Z. And from here, you know that the lambda is proportional to the scale factor, so it is not very difficult that you can show ultimately that the redshift is basically at any point. So if there is an object at a scale factor when the universe scale factor is at A equal to emitted, and you receive that light at a scale factor today, let's say at A equal to 0, then that light get redshifted, and that redshifted is given by this. So if you can measure this redshift, it actually can give you an idea the size of the universe compared to the present size of the universe. Okay. And because we know that the universe is an expanding universe, this can also be used as a sort of a time stamp in the universe. So we can, instead of time, we can use this redshift as a sort of a time, fine. And it also shows that early, as you go early, so this redshift is positive. Today the redshift is 0 because these are same. So 1 got cancelled, the today redshift is same. As you go early, the redshift is greater than 0, okay? So that is the thing that we will use for the redshift. In general, what we do most of our cases that we normalize the scale factor today at 1, so that makes a lot of writing to get shortened up. So we will assume that at present the A0 is 1. In fact, that you can do because once you write this thing, you can show that I can just scale A as, let's say, like A as a some lambda A, and we can then scale K and R, all those things properly, so that this has a sort of a scaling symmetry that we have, and that I can use to set A equal to 1 at today, okay? Once we do that, then any point, if the scale factor is A, then the redshift we write just like this way, okay? So that will be our the formula. But if you are not comfortable, you can always put this. Okay, so that's fine. So that's the another observable thing that we use for our cosmology, which is one of the very important thing. Okay, so once we have this initial thing, then what we usually do that we write down the Einstein's equation. So the Einstein's equation of general relativity to write the equation of motion for the cosmology. Okay, for the expansion of the universe. So so that we all know that we have to write down this equation. We have this, the equation that we have. Okay, so we have to write down this equation for this thing. So we have to calculate the g nu mu's for this metric, given that there is only one time component or time function, which is the scale factor, and the t nu mu we have to assume. Okay, remember that we have to assume a t nu mu which has to be consistent with homogeneity and isotropy. Okay, so that's the thing that we need to assume. So homogeneity means there should not be any space dependent in the t nu mu, because all the energy and momentum, they will be same at all space location. So there should not be any space dependent. And the isotropy says that the three space part should be the same. Three direction, theta direction, phi direction, r direction, they should be the same. Fine. So, so that actually gives you that to be consistent with the homogeneous and isotropic universe, your t nu mu, so t nu mu or t nu mu, let's say we write it in a mixed form. So I am using a convention plus minus minus minus. So in this convention, my t nu mu will be rho minus p and minus p, and all other parts are 0. Okay. So what we do, we calculate g nu mu from this, and we t nu mu assume means these are all function of time. So this is the form that we have with consistent with the homogeneous and isotropic universe. When you do the perturbation, then we no longer assume this. So this can get space dependence. This can have anisotropy. So that we need to consider. But for the time being, background cosmology, homogeneous and isotropic, the t nu mu has this form. So with this structure, so we write down the Einstein's equation, and and the Einstein's equation, okay, I am not going to I just write down the Einstein's equation. So there are two Einstein's equations that are there. One that measure the first derivative of the scale factor or the velocity or the Hubble parameter. A dot by A is the Hubble parameter. So that equation is this 8 pi g into rho, that thing that we have. And the second equation is actually the acceleration equation. Sometimes we also call this the Roy-Choudhury equation. So this actually gives you the acceleration, the second derivative of the scale factor, and this is okay. So remember, these are all function of time. Okay, so and these A's are also function of time. So these are the main two Einstein's equations that we can get. So this gives you the velocity and this gives you the acceleration. And as you know, the acceleration in gravity is a kind of a force. This is related to some kind of mass. And this is, in a sense, the kind of a mass that we use. Okay, sometimes we call the ADM mass or something. But so rho plus 3p. Okay, so that is the effective. You can call it an effective mass that gives you that force of gravity that gives you the acceleration. Okay. So these are the two equations. There is another equation which is not independent. But which can be formed from here, or which can also come from the energy conservation, because we have an energy momentum. We all know that this g nu mu has a Bianchi identity. Its divergence is 0. So that gives you the t nu mu divergence is 0. And if you use the t nu mu divergence 0 with this metric, we get another equation. That equation also we can get assuming that the universe expansion is adiabatic. So that change of entropy is 0. From there you can also use it. Fine. So whichever you use, so that equation that you get is this equation. Okay. H is my A dot by A. Okay. So these are the three equations that, that we mostly use for all the background cosmology, or in the perturbed universe also we use the perturbation or the perturbed version of these three equations. Okay. And as I said that only two of them are basically independent. The third can be calculated using the other two. Means you can use these two to get this, you can use these two to get this, or so on and so forth. Fine. Okay, so these are the three equations that we usually use, and just from here we can actually get something, from this equation, which is interesting to know, is that let's say so let's say you have this A over this direction, okay, A as a function of t, and you have some direction, there is a time, and let's say today is t naught, which is at present time, let's say, and at this time, so you calculate, as Robbie was saying, we have a Hubble parameter, fine. So we know the h value, so we know the slope or this A, fine. So let's say so here we know, let's say a dot, which is the Hubble parameter, fine. So this slope, let's say we know, fine. And if this slope, if this Hubble parameter remains the same, so we can draw a straight line, and it can cut at some point at this time, fine. Okay. And so now, this is, now what is this? This thing? This is the scale factor at today, fine. So this is the scale factor at today, which I fixed to be 1, but let's put it a naught, fine. So this is the scale factor, this thing, okay. And what is this? More age of the universe, but I have given you a dot. So what is this in terms of that? A by h. So 1 by h, fine. So this is 1 by h, fine. Very good. At present, fine. This is 1 by h naught at present, fine, or h naught. Okay. Okay, that's good. So now it says is that, so now if your h remains the same, or rather your a double dot is 0, because a dot is a constant, then it just goes like this way, fine, straight line, fine. But if your a double dot is negative, then it should have here some slope over here, but after that it should either go like this way or whatever, depending upon whatever your the parameters, fine. So it cannot, so it could go up to this if this is negative or less than or equal to 0. It can go maximum up to this, or it can go cut any time here, fine. On the other hand, if this is positive, so it can go like this way, fine, the other direction, fine. So what it says that, let's say that if we have a universe which is dominated by rho, some energy density, which is always positive because it's energy density, and some fluid which has a pressure for which rho plus 3p is positive, and we'll see that most of the normal matter that we can see of, that Robbie was talking about, baryons or matters, normal dark matter or radiation, all those things are the pressure positive. So matter or baryon we can put it to 0, for radiation we can put it to 1/3. So this is always positive, then it is always negative, and then it always hit here at some point. So this says that with the normal matter, the universe, the scale factor goes to 0 at a finite time at any point in the first, fine. And the finite time, the maximum finite time can be 1 by h naught, or it can be less than 1 by h naught, fine. So it always gives you that with a normal matter that I have at some point the scale factor goes to 0, okay, at finite time in the past. And then we'll show later very quickly that when the scale factor goes to 0, all your physical quantity like physical energy densities for matter or radiation, they blows up. So there is a singularity, okay. So that is a finite path that we have where you hit a singularity, means things blows up, and after that things goes with a means expansion universe with a decelerated way because the a double dot is negative, okay. Only way you can avoid this, is that instead of this slope, it just goes like this way. And to go like this way, you need, this has to be positive. So some strange kind of thing has to be here, so that this rho plus 3p is negative, so that these become positive, and these guys looks like go like that way. So for normal matter, normal radiation, you always should have a time or a finite time in the past when things can, the scale factor goes to 0, and quantity like energy densities and those, they will blow up, okay? They will go to infinity, okay? Okay, that's fine. So now what kind of quantities, what kind of this rho we can have? So we can have non-relativistic particle or non-relativistic fluids. And when we take non-relativistic, we assume that the rest energy means the pressure, which comes from the kinetic energy, which is much less than the rest energy or the energy density or the rho. Fine. So we can ignore pressure compared to the energy density or the rest energy density. So for the non-relativistic case, we can assume this pressure to be 0. It's not pressure to be 0. It basically pressure is much smaller than, I am putting C equal to 1. So pressure is much smaller than the energy density. Okay. And if you have a radiation like photon or massless neutrino, okay. So these are, which one?
Rho is much bigger than P.
Oh, sorry, yeah. So for radiation, so your the pressure is actually 1/3 of rho. Okay. This you can calculate for the radiation. These are traceless field. So if you calculate the trace, which is rho minus 3p, which is equal to 0, that gives you the pressure is 1/3 rho, or you just write down the distribution function. You can calculate from the distribution function also. Okay, so these are the two main fluid that we have in our universe. Fine. All the matter or baryons, so we can assume them to be non-relativistic and they are pressureless. And the radiation like photons or massless neutrinos, they have a pressure which is like 1/3 rho. In general, we can have any pressure, we can have an equation of state into rho, and depending upon that W, where here the W is 0, here W is 1/3. I use this thing because, as Robbie was pointing out, for the dark energy, we have this W, which is not 0, which is not 1/3, which is negative, and it has some bound from observation. Fine. One of the main interesting ingredient of dark energy, which is cosmological constant, for which W equal to -1, or pressure is minus rho, P is minus rho. Okay. So mostly, I think in all our lectures, we'll use this part, and this part, taking that the other three. But you can easily generalize that. You take a component like this and you use those things. Okay. So that's not very difficult. Okay. So that's fine. So once we have these things, so if I put all those things in this case, so what I can get is that for non-relativistic things, the energy density scales as a to the power -3. Here it scales as a to the power -4, and here it is a constant. Okay, and that Robbie told that for non-relativistic case, it just scales as a volume, and for radiation, it scales as a volume, but extra there is the energy which is redshifted due to the expansion of the universe. So there is an extra 1/a factor because the lambda goes as 1/a. The Z goes as 1/a. So that factor gives you an extra 1/a factor. And for CC, the dark energy, you can see that rho equal to -p, so this term vanishes. So this rho is just a constant. Rho dot is 0. Okay. So these are the three main components that we can have, and okay, and from here, as you can see, that that Robbie said that this at some point in the past, so if dark energy is very small, so it is a constant always. So let's say I am doing a log rho by log A. So dark energy is always, let's say, a constant, okay, and very small. So it is there. And these two actually scales with a two defined way. So one scale like this and another scale like this, fine. So at some point in the past, the radiation always dominate, And at some point, the matter start dominating, but all of them get redshifted, or all of them get diluted due to the expansion of the universe, but the cosmological constant remains constant. So at some point in the future or some point, the cosmological loss means naturally the cosmological constant will dominate. You cannot stop that, fine. It may not be today, or in the future, or in the past, or maybe in the future, but it should dominate at some point of the time, because these two are diluting, this remains constant, okay? So this is cosmological constant. And one important epoch, I think, in our structure formation that will be used is the epoch of the matter radiation equality. So that is an important epoch, the matter radiation equality, okay? So it's just the epoch when the scale factor, when the matter and the radiation, they become equal, okay? And that you can calculate easily. So you can see that the matter goes like some initial matter to the power A3, and the radiation goes like some radiation initial to the power A to the power minus 4. So if let's say at equality, these two are equal, so rho m at equality equal to rho radiation at equality, and that you can give it that rho m naught A equality minus 3 equal to rho naught A equality minus 4, and this gives A equal is rho today value and this thing, fine. So if we know what is the amount of radiation today, what is the amount of matter today, I can know the scale factor at which they are equal at some point in the past, okay? We'll just see that once we define the, usually we don't measure this, we measure what is called the density parameter. Density parameter for radiation, the density parameter for matter, and then these are actually the ratio of the density parameter of the radiation and the density parameter of the matter, okay? This is roughly around 10 to the power minus 5, this is roughly around 10 to the power minus 1, this is roughly around redshift around 10,000 or so, something, okay? So that's another quantity that is used, okay? Okay, so these are the equation, and so another thing that we'll use is what is called the density parameter. Which is an observable parameter. Okay, this is defined as for any substance I or any species. This is rho I by the rho C, and rho C as Rovi has already defined, the rho C is 3h square by h by g. Okay, so this is the density parameter, and this is the critical energy density. Okay, today this value, if you put h naught around 70 kilometer per second per megaparsec, and h g value, this is roughly 10 to the power minus 29 gram per cc, something like that. So this is the defined density parameter, and then with terms of this density parameter, what you get is your okay. So what you can write your Einstein's equation, the first Einstein's equation, as h naught square into this rho m naught to the power minus 3 rho 1 naught to the power minus 4, then rho whatever, let's say lambda, okay, plus rho k naught the power minus 2. Okay. So for omega k, we define the density parameter a little bit different way. So omega k we defined as there is a, you know that, okay, this equation I wrote, okay, I'm sorry, this equation I wrote for the flat universe, assuming that the universe to be flat. Otherwise there is a 3k by s square. Okay. There is a 3k by s square, there is always there. Okay. So we define so that part is, so just make it thing. So this is a 3k by h square. So what we are doing, if you remember when we are doing it, so we are putting the matter which is rho m naught a to the power minus 3 for radiation, which is rho m naught a to the power minus 4 for cosmological constant this, and then there is a h square term over here, and I am dividing everything by 3h naught square, which is the rho c naught, the present day value of the critical density, like this way. So I am just dividing that. So when I am dividing this 3 by h naught square, so what I get, this omega k naught, which is minus k by h naught square. Okay, so that is my omega k naught. So this is the equation that we have for Hubble parameter. This equation, we will see that we will use this equation for most of the, for all of the geometric quantities like co-moving distance, luminosity distance, angular diameter distance, the volume or whatever. And in fact, if you want to do the linear density perturbation, there also the thing that we need is the h as a function of a or function of z, whatever. And this is the h expression that we use. Fine. We'll use this expression. Okay. And as you can see that it has these quantities like matter, what is the amount of matter that we have, what is the amount of radiation that we have today, what is the amount of cosmological constant, the curvature, amount of curvature that you have, and also the present day Hubble parameter. So all these geometric quantities, they depend on these parameters. Fine. But there is one thing at present, as I said, this A is 1, A is 1, A is 1, okay, and this H is H naught. So what we know that at present is if you add all those things, this gives you a 1. So not all the 4s are independent. If you know the 3, you know the other one, fine. So that's the thing. And if you assume that the universe is flat, which we can actually from the latest CMB measurement where the curvature is determined to be very, very small. So then we can ignore the curvature part, and then these 3 are related by this, that so that their sum is always 1. Okay. And also again today the amount of radiation is extremely small. So what actually govern the present universe or universe very near to the present time is the matter part and the cosmological constant part. Okay. So that we have. What else that we have? And maybe we'll need at some point that we define another quantity from here. So this is the h, fine, the velocity. This is the acceleration a dot by a double dot by a, and using this acceleration we define a parameter called the deceleration parameter. Okay, which is and this is minus a double dot by a by h square. It is deceleration because the minus sign is there. Okay. So q positive means a double dot negative. That means there is a deceleration, and q negative it means this is negative, so there is an acceleration. Okay. So if you can measure this q at any point, let's say at present time, okay, q naught, so h naught and this at present, and you get a value of q naught which is negative, then we can say that the universe is accelerating, or means whatever. Okay. So this is one important parameter, and this parameter actually you can write from here. I am not going to derive that thing. You can use all those quantities and you can divide it by h square and you can write this parameter. Okay. And this parameter, if you write in terms of these and all those things, remember that here one thing is interesting, that the acceleration doesn't depend upon the curvature. So with a specially curvature, means instead of flat you put a spherical universe or a hyperbola, it doesn't change your acceleration. So in the acceleration, curvature doesn't take place. Okay. So one can write down things, and specifically this q naught, if you do a little bit, a few lines of calculation, this comes up to be half omega m naught plus omega r naught minus omega lambda naught. Okay. So if we can now measure this amount, we can say whether the q is not is positive or negative, giving the fact that there is a consistency relation like this way. Okay. So one can do one thing. One can do one thing, that let's, for the timing we calculate things, we measure things, and at the present time the amount of radiation is very small. That you can expect, because this is a constant, this scales as 1 by a cube, this scales as 1 by a4. So at the present time this is much smaller than the other term. So we can, for the timing, let's ignore the effect of radiation around the present time, and then you try to plot, let's say this side omega m naught and this side omega lambda naught. And as you can see that if, so this is for the timing I am ignoring, this I am ignoring. So if q naught is 0, means a double dot is 0, that means the Hubble parameter is a constant, fine. So then that means that your omega m naught is twice of omega lambda naught, or omega lambda naught is half. So there is a straight line with a slope of half, fine. So that actually has like this kind of line, fine. This is q naught equal to 0. This side will be q naught less than 0, and this side will be q naught positive, fine. So this side, the straight line, this side will be a accelerating universe at present, and this side will be a decelerating universe at present. Okay. And if you, for the timing, this is this. So if there is no curvature, then omega m naught plus omega lambda, which is 1. Okay. So this has some sort of a line like this way. Okay. Some sort of a line. And then if you have a curvature, this can be, if you remember, this is negative k. So k positive means this is negative. For spherical universe, k is positive. So omega k naught is negative. And for hyperboloid, so this is negative, so this is positive, fine. So then depending upon that, so if this is your flat, which is for omega k naught is positive, then this side will be an open universe, and this side will be an closed universe. Okay. So what, as Ravi was saying, that what the observation says, that around today, this comes out to be over here, okay, where this is around 0.7, this is around 0.7, and this is around 0.3, okay. There is some small error but over here, obviously, there is some small error but over here, but roughly like here. And as it says that the universe is flat, and this is q naught negative side, so it has an acceleration. So
what is the physical significance of omega k?
No, omega k is just a parameter that we means in general there is a square, but for the time being a I put it 1, but it measures the amount of curvature. Okay, so this is the k 0 means the omega k is 0. Okay, if k is positive, then this is negative. If k is negative, this is positive. This we don't measure directly. What we can measure is that we measure this, and then we see that whether this comes out to be 1 or comes out to be less than 1.
You're measuring it along with matter, radiation, and dark energy, right?
No, you are inferring the curvature.
I am inferring the curve. Means I am not measuring it directly. You can measure it, as Robi was saying, that you measure the angle. So if you have a rod over here, okay, and here you are here, you measure the angle that I will discuss just after a few minutes. And depending upon this angle, so for a flat universe you have an angle. For an open universe the angle will be smaller. For a closed universe the angle will be larger. So if I can measure the angle, I can infer whether the geometry is positive, means geometry is flat or spherical or hyperboloid. Okay.
So is there an inherent energy term because of the curvature? Like for example, matter, radiation, and dark energy are providing.
Yeah, so that if there is a special curvature that is there, if you can calculate the gravitational potential, that gravitational potential will be different if you don't have a curvature over here. Okay, but remember one thing, the crucial thing is that the acceleration doesn't depend upon the curvature. So it just comes in your energy constant equation, what is the sort of a total energy constant equation. The acceleration doesn't depend upon the curvature. Okay, so the second derivative of the scale factor doesn't depend, but your velocity, so the kinetic energy that you have whole, fine, so this has a dependence on the curvature.
Omega k is just reformulating the curvature parameter in terms of the dimensions of energy. Right?
No, that's true. So all those things are like that.
That's what
Means all the density parameter is that instead of this density means actual energy densities, you are writing a dimensionless quantities, so that means you can observationally detect it. Fine. So omega k is same like that. Omega k is same like that you are defining a dimensionless quantity, but it has the information about your the spatial curvature. I mean in a way that all of these things are there. So means you can say that this has you can consider that this is a term in the energy density which scales as 1 by s square. Fine. So if this is non-zero, so at some point in the past, very early time first, means like this is dominant first, then this will dominate, then this will dominate, then later on the cosmological constant dominate. So if there is a special curvature which is there, at some point of the time the expansion of the universe will be dominated, will be governed by the curvature, that you can see, because this 1 by s square at some point after this it will start dominating. Fine. So if there is a non-zero curvature, obviously the expansion, in fact, we'll see, or if I can have time, the age depends crucially on the curvature, and there is a age problem in the universe when the late time acceleration was not detected, and initially people are thinking maybe an open universe can solve the age actually, because in open universe you can have a higher age than a closed universe. But okay, the other observation obviously said that the curvature is 0. Okay, and with dark energy we can actually get the right age. You have any comment? Okay.
Yeah, I have one question. For first line, you are putting a Q0 equal to 0, no? Q not equal to 0.
Which first line? Here?
Yeah. But what about I have missed that point. What about the second you have drawn that graph?
This graph, this curve.
Yeah.
This is here. So I am both of the cases I am ignoring the radiation. So you have omega matter, cosmological constant omega, and the curvature. So if the curvature is 0, which is specially flat, then omega matter plus omega lambda is 1, which is this line. Okay. Quickly. So this part is fine. So now I just quickly define the defined distances. So the first distance is the co-moving distance. Okay, so you just assume there is a light propagation. So your ds square is 0, okay, and we take to make the calculation simple, we just take a equatorial plane, pi theta equal to pi by 2. But as you know that the universe is isotropic, so if you put theta equal to pi by 2, get a result. This result is equally valid for any other direction because we have an isotropic universe, right? So you assume theta equal to pi by 2, we just concentrate in this plane, and you assume that the photons are coming radially, fine. So there is no change in phi, okay? So phi is constant, fine. This is coming radially. So then what you get is that if you remember ds square, so you get that dt square equal to s square t dr square, and that you get dt equal to plus minus at into dr. And as you got the photons are coming radially, with time the dr actually the distance actually decreases. So we take this the minus sign, and then your dr is minus dt by at, and you integrate it out. Let's say you integrate it out, I mean let's say at dr at some point at r naught to today you are at the origin of your coordinate system, okay, so that's there. And for initially when say time 0 to at the present time, or I mean when it was emitted, so let's say you just fix the time and then you take the time, or let's say at emitting time it's a ti to t0, okay. So that's the thing that you see. So this is, so you take the plus minus sign, so this you can make r to mean 0 to r, so this minus sign goes. So what you get, your comoving distance is some initial time to at today you go dt by at, okay. You can change this a little bit. So we know that 1 plus z, the redshift, which goes like scale factor. So I can use this term, I can use this thing because this dz dt is minus a dot by a square, which is minus h into 1 plus z. So I can write dt in terms of dz, okay, and 1 by a is 1 plus z. So I can do a little thing, and then what I get is that this is equal to, let's say 0, and at the time when it is emitted the redshift is, let's say z, so this comes out to be dz. So this r this is the comoving distance. From u to an object when the light was emitted and the object is at a redshift z, okay. And as you see that this just depend upon hz. Hz we write in terms of omega m naught, omega r naught, omega lambda naught, and 1 by a cube, that you can write as 1 plus z cube, 1 plus z4 and all those things. So h as a function of z we can write which has the parameter h naught, which has the parameter omega m naught, omega lambda naught, omega r naught, and if there is a curvature. If there is a curvature, this I am assuming there is no curvature as a flat, okay. If there is a curvature, so if you remember there is a 1 by k r squared term. So in that case here there will be a square root of 1 by k r squared term where k can be positive and k can be negative. So in that case this r will be either sin r or sin hyperbolic r, and in that case this r will be sin inverse of this or sin hyperbolic inverse of this, okay. So to make life simple, I am just for the time being doing the flat case, okay. So this is the comoving distance, and this h just depend upon all those quantities, h naught, omega m naught, omega lambda naught, omega r naught, omega k naught, fine, okay. So knowing those things we can calculate this comoving distance. So once we know the comoving distance, which is this, okay, just remember this, we can calculate what is called the luminosity distance. Okay, so the idea is simple, that if you have a standard candle which has an absolute luminosity, okay, which at some point in the universe at some redshift it is there, and then it is emitting light, okay, in all direction, and you are here, okay, at a say t equal to t naught hypersurface, so you receive light for all these sort of a cone, fine, uniformly, means isotropically distributed. So the apparent flux that we received will be this L by 4 pi r square, fine. So this is the luminosity and this is the luminosity per unit area, which is the apparent flux that we receive, fine. So this is the standard case. Only in our case the difference is that this R that we have is not fixed, this is changing with the expansion of the universe, fine. So that is happening, okay. And this R is now, so if this thing is here, so R is just this co-moving distance that we have calculated just now, which is the integration of dz by hz. But there is also two things happens, because this luminosity that when you calculate, first this is the photon, so these are the energy E h mu, and as the universe expands, so this energy get redshifted. So this luminosity also has a redshifted term by 1 by A, so that is a 1 by z factor that is there, okay. Another, this is the energy per unit time emitted, fine. So the time period that we have when it was emitted and the time period that you have when you received it, that also actually gets changed due to the expansion of the universe, and that also get changed with a 1 by z factor. So there is a 2 1 by z factor that comes. One is due to the photon get redshifted, okay, that is 1 by z factor that comes, and another 1 by z factor that comes is due to the fact that this is energy per unit area, and this is energy per unit area energy per unit time, and then energy per unit time per unit area. But the time that the photons are emitted, that from here to here due to the expansion of the universe, that also gets changed. So there is also a factor that comes due to the expansion of the universe. This R into 1 plus z, this is called the luminosity distance. So that is the thing that we plotted for the supernova. So remember that is R again, this R is always 0 to z dz by hz, and this h has all the information of omega m naught, omega n naught, omega lambda naught, or omega k naught. So if you now have this supernova that we have, so there I can, if I know supernova as a standard candle, so if I know its absolute luminosity, which we don't know exactly, but let's assume that somehow we know this, and then we know their apparent flux, fine, that the flux that we measure, apparent flux, and from there I can know their dl, okay, from this expression, okay. And we know the dl, and then different means the light that is emitted from the supernova, they get redshifted. So you know those redshifted light, we can measure their redshift, and redshift means the velocity actually. So we can draw the Hubble plot, which is the distance versus the velocity, and we get the slope, okay. And that the plot that Rovi showed, that is initially straight line and then it just actually curved, so that it's actually decelerating early time and then started accelerating today, okay. But the main factor is that if we have a standard candle like supernova, which has some, which we believe that we know its absolute luminosity at some level, and then if we measure its apparent flux, then I can measure this dl, and this dl contains the information for h, and h contains all the information about different cosmological parameters like h naught, omega m naught, and all those things. So by these experiments, these observations, we can actually constrain all those cosmological parameters, okay. So that is the luminosity distance, which is a kind of a standard candle, okay, that we use.
So you will find the R from your observations, and then
we find the dl from the observation.
Find the dl and try to fit the function for h.
Then fit the function for h, for which the omega m naught and omega lambda naught actually give you a base fit for the observation. And from there, as Robi said, that 0.7 and 0.3 is the sort of a best fit, okay, for that. And if you put then again 0.7 and 0.3, this gives you that n over naught is negative. So that gives you that the universe is accelerating. Okay. Okay, so this is the luminosity distance. So this takes care of the fact that we have some sort of a standard candle in the universe, okay, for which we can measure the amount of photon, okay, the apparent flux. Okay. There is another distance that also Robbie will use, I think, a lot, which is called the angular diameter distance. So this assume that we have a standard rod in the universe and we measure its angular scale, or its what kind of angle it subtends at you. Okay. So let's say you have a standard rod over here, okay, which is, let's say, at some time t, okay, at a co-moving distance r, okay, and at a some phi, and with theta here and theta equal to some theta plus d theta over here. Okay. So these two things, okay, and you are here and oh, sorry. So this is your d theta. Okay. You are here at, let's say, t equal to t naught, that you are sitting over here. Okay. This is the length of this rod, okay, that we have. So the angular diameter distance dA is this d by this d theta. Okay. So that you have. But now take your ds square. Okay. Now take your ds square. So this ds square here. So for this, let's say I am just writing what is the distance. Okay. So this is at the same time. So dt is 0. Okay. So this dt is 0. This is at the same r. So the dr is 0. The d phi is 0. Only term that over here is actually r square d theta square. Fine. S square r square d theta square. There is a is there sitting outside. Fine. So that term is there. So your length, that the spatial length, because the time is 0, that at the same time the spatial length that we have is s square. Okay. The co-moving distance r square and d theta square. So this is the length actually that we have. Fine. Which is this d. Okay. So d square rather. Okay. So your d is basically a r d theta. So d by d theta is a r. So your angular diameter distance is a r. And if you remember, my a is 1 by z. So this is r by 1 by z. Okay. So again, remember this r is 0 to z dz by hz. So this also again contains all the information about cosmological parameter. So now, as I said, that if you have a standard rod in the universe, let's say in CMB the acoustic scale, which is there at the redshift around 1000, okay, it subtends an angle to you, okay, and from there you can calculate its angular diameter distance, and you see that whether it matches with that Robbie said that the angular scale of 1 degree separation, whether you get it or not. Fine. The same you can apply, maybe Robbie will talk a lot about the Baryon acoustic oscillation. So there also you have oscillation and you have an acoustic scale, Baryon acoustic scale, okay, and that acoustic scale that also sets a angular scale with an angular diameter distance, and that again gives you, once you measure this thing, this gives you a strong constraint on the cosmological parameter. And interestingly, if you do constraint, let's say omega m naught and omega n naught from this dA, and you do the measurement of omega m naught and omega lambda naught from dA, and omega m naught and omega lambda naught from luminosity distance, they are actually orthogonal to each other roughly. So that's why if you have the contour like omega lambda and omega m, okay, if supernova as a standard candle give a contour, means if you measure this dl and it gets a sort of a contour like this, the baryon gives you, baryon acoustic oscillation can give you, or CMB can give you a contour like this. And that's why you can get actually a very strong constant when you combine these two things on your cosmological constant and the matter, okay? You can constant your universe a lot. So these are the main, the co-moving distance, and corresponding to co-moving distance, the angular diameter and luminosity distance. They are the two main distance indicators that we use for the geometric probe. What else?
So actually, sometimes I found it difficult to practically visualize both of these distance measurements. Means in case of luminosity distance, if I'll plot luminosity distance versus redshift, then at a redshift around 1.2, I'll get a number luminosity distance around 10,000 megaparsecs.
But that depends upon what cosmology you are using.
No, it means if for the 0.3, 0.7
Okay.
case. Now, secondly, if I'll think that the light is coming from the very beginning and the age of universe is around 13.7 billion years, and the total distance traveled by a photon in this distance would be hardly 13,000 megaparsecs. Means a distance, luminosity distance at z equal to 1 or 1.2, it's around 10,000 megaparsecs, and the whole distance traveled by a photon if coming from the very beginning, it's hardly around 13,000 megaparsecs. Means how to visualize this thing?
How to visualize this thing? No, that you can see, because if you take h, fine. If you take the h and you do the co-moving distance measurement, fine. If you just do that measurement, this, okay. If you just calculate this, fine. So you can see, let's say I calculate these to z0 to some redshift, okay. Redshift infinity is that from the very beginning to till today. But you can see from here itself that if you measure the distance or the amount of things that contributes to the co-moving, mostly things contribute from very low redshift. Before that before that the things doesn't contribute that much actually, because your omega m naught and means 1 plus z cube, 1 plus z4, all those things if you put and if you integrate things, the main distance that actually matter, means the contribution of main distance, is basically between 0 to 1 or 0 to 2. Before that, there's not a much of contribution from there.
And similarly, in the case of angular diameter distance, if we plot it, then around similarly for 0.3, 0.7, we get this change in the kind of change at around redshift z equal to 1. It suddenly start decreasing. Means I didn't get the, if I'll plot the, it will increase up to redshift z equal to 1. Then if I'll plot it up to 1.5 or 2 redshift, then it start decreasing.
This is, so from redshift 0, it will, what you were saying? This is like this. No. Oh, sorry. This is like this.
Yes.
Yeah.
So I didn't get the, why did it get turned down at around z equal to 1? What happened to this thing around 1?
Is it will always z equal to 1? Means
For 0.3 and 0.7, this is the case.
no, obviously if you fix the omega m naught and omega lambda naught, that redshift when this will change, that will be fixed. Means that will be maybe 0.1, that I don't know the number. But if you change your parameters, this can change. This can definitely change.
For any possible case. Why does it change? It means if I have a standard rod and it's moving from redshift 0.1 to 0.2 and then at redshift 1 and then at redshift 1.2, let's say. But what happened, this angle should continuously decrease. But what happened that suddenly at z equal to 1.2 or 1.
But that will depend upon, I think that depends due to the fact, is it due to the acceleration? I think this is the acceleration, fine. Because if you don't have dark energy, then that will not do, you don't do these things. Once you have this dark energy and the things started accelerating, and it depends upon at what point the dark energy start dominating, then it will change the slope. isn't it, or what? With a one means only decelerating universe, will it go and change the slope? It only change the slope, as far as I believe, is basically due to the when the acceleration starts dominating.
Actually, this counts because we normalize at present time h not equal to constant for all the models. That's why if I plot h by h lambda CDL, the things will be like this.
No, that's fine. I mean, that's the thing, but that this change, what he's saying that a change, this is due to the fact that the universe started accelerating.
Yeah.
Or no?
No, for Einstein Tensor, this is something we can work out. No, I think it's.
No, if it is always accelerating, or Einstein de Sitter you are saying.
Yeah. So there's no cosmological constant.
No cosmological constant. So let's say only matter. Because if you have, let's say, only 1 plus ZQ, fine. So this will be only one dependent. There will be no maximum or minima, fine. Like omega m naught and lambda, then it change. If you have only omega m 1 plus ZQ, fine.
Because the transition from deceleration to acceleration it's around 0.7, but it's around 1.2. Then I found it difficult to correlate
With these numbers, one has to look at the number. I readily I don't. But the fact that it can change the behavior, it's basically due to, because if you have only matter, then you can see that if you have only matter, let's say, so this is 1 plus ZQ, fine. So then you integrate it, there is no maximum or minimum, fine. Only thing it will happen that if you have a term over here, another, let's say omega lambda, then it can give you, depending upon omega lambda and omega m, it can have a dependence over here, fine. I mean, this kind of non-monotonous dependence, fine. But where it is exactly happening is which point that, I mean, that the value, I think, and then it may not be exactly when the acceleration starts. I mean, at some combination where the different terms get, yeah, then, yeah, so.
Is it giving any information like it is increasing and decreasing first? Is it giving any information about physical information?
That may be due to the acceleration, fine. So you have some rod you set, you have a decelerating universe. So the way it actually changes, fine. And then suddenly the universe started accelerating, the expansion is accelerating, okay. So that gives you, that gives you maybe some, I never, find out it out, but I think that can give you an idea that when from deceleration to acceleration switch over and how this dA actually depend upon that. Means how the dA depend upon from switch over from deceleration to acceleration. But that, okay, that I will check because this I have not checked any time. You have any clue about that?
Yeah, not for that number.
But any clue about during acceleration it will change this thing? Okay, so we'll just check it and then. Okay, so I'll stop here. If you have, these are the things that I was supposed to tell. So I stop here. If you have any question, or in the tutorial we have, so we can discuss. We'll give you some material. There are a lot of cosmology books, but some of the things that may be useful that we'll give.
There was one last thing that usually comes with this, which is some people define the surface brightness.
Okay.
Right? And so that one will be L by R squared. And if you observe a brightness and you observe an angle, then the observed surface brightness will be the brightness divided by theta squared. So the relation between the observed surface brightness and the true one, to go from brightness to luminosity, there will be a luminosity distance squared. And to go from theta to size, there will be an angular diameter distance squared. So that means there are 1 plus z squared with the luminosity and squared with the angular diameter. So there's a 1 plus z to the 4 for the surface brightness. So when people first derived this stuff, they thought maybe because 1 plus z to the 4 is true for all cosmologies. So they thought this is a nice test of Friedman-Robertson-Walker metric. If you know that galaxies all have the same surface brightness, L by R squared. In fact, galaxies evolved, so it turned out to not be such a useful test. But people still have in the back of their head that maybe they can find some population they can do this with. Constant surface brightness, and then you can do this. It's called the Tolman test.
But brightness and luminosity is constantly changing, no? Because the reaction is going on in stars and galaxies, and it's a function of time, no?
Yeah, that's right, that's right.
Yeah.
But I'll give you not a good example, but you can see the idea. So supernova is L is the same, right? So if you could resolve the supernova, then L over R squared,
Yeah.
presumably.
Yeah, that is,
So
but that is
now-
an exploding star, no? Means
No, that's a very strange thing. I
Yeah.
understand. But it could be that we can find some kind of object
Yeah,
that this could be applied to. So the hope was, people never imagined that we would see to redshift 100. No? So seeing to redshift 0.5 or something, they thought maybe objects don't evolve.
yeah.
So what about the point objects like quasars at redshift 6? So how do you determine these distances for those?
So that is the luminosity distance. Because, so you use the luminosity distance for the brightness, and you have to, if you could resolve the size, then you would use the angular diameter distance.
But the luminosity can vary with depend on the redshift. Because quasar formations peak is around redshift 2.
Yes.
So if you are talking about the 4 and 5, so there will be different luminosity.
Yes.
Then how do you fix this?
How do you fix?
Like because luminosity is not fixed for all the quasars.
That's correct, yeah.
So it can vary with redshift.
Yes.
So, and they are point objects. We don't know the actual redshift.
Actual physical size, yeah.
Is this good method to determine the distance for those objects as well?
To determine the distance for them? No, because they're not a standard candle.
So up to which redshift, like we can use these in distance?
But it depends.
I guess you use it the other way around. So with the quasar, you observed a flux, you observed an apparent brightness. So how do you know what is the luminosity? And you use this to find out what is the luminosity. Because you measure the redshift, but you have to know the cosmology, then you know the redshift. You don't do it the other way around.
Okay, so you know the redshift and you know the apparent brightness, then you go to the back. Okay.
You must know the cosmology, then you can do it.
But if we know, if we consider GRBs to be standard candle, even then we can calculate these distances up to redshift 3 or 3.5.
Yes.
But for that we have to assume that GRBs are standard candle, which is not proved or.
But what I feel that as we go deeper and deeper, then our distance means the method to making it. Yeah, distance ladder which you have mentioned, no?
That's right.
So we cannot say that this is means the standard method to measure the distance in cosmology. Means with varying rate that Z.
Yes, but so let's distinguish now. So this is always correct. This is always true. But now the question is, how do you use it? And so with the distance ladder stuff, that was what should you do if you don't know the cosmology? Right? Because to apply this, you need to know the cosmology. It depends on the background cosmology. And so that was trying to say, can you find some standard object or something like this for which you didn't need to know the cosmology, so you can learn the cosmology.
So in this rho lambda, you are assuming it to be constant. What is the reason behind it?
Which one?
The last
Here.
the energy in the like rho, the energy density of it.
Cosmological constant.
No. Rho lambda.
Rho lambda, na?
Yeah, you are assuming it to constant.
No, that you can see, no? Because it has the equation of state -1. P equal to minus rho.
But it can vary with the like. Why we are assuming it to be -1? It can vary with redshift as well.
No, if it is a pure cosmological constant, if you have a pure cosmological constant, which is, we can say that it is a vacuum energy of a ground state of a field theory or whatever, fine. So there means there for that case, the W equal to -1. Okay, you can calculate. But as you said, it's right. Means this cosmological constant, what you are saying a cosmological constant, it may not be a pure cosmological constant like what we put, fine. Where is the chalk? So when I'm saying C is cosmological constant, I am assuming that there is a fluid which is this. Okay, which is a fluid like this. But there can be other cases, there can be cases where this P is not exactly minus rho, but where the P can be some, means W is there, the W has some value or some, say scalar field, fine, where the W can be evolving with time or whatever. So that, for that case, things will not be a constant. This is only a constant for a particular case of cosmological constant, and Einstein put it, or what you can get this, the Zeldovich and other people have calculated that if you have a field theory, the ground state or the vacuum of that field theory has a structure of energy momentum tensor T nu mu, which is lambda delta nu mu. Okay, so or T nu mu is lambda G nu mu, whatever. Fine. So for that case, that particular case, this is a constant, not for us, not for all. But I think in our case, we will not do that complicated other cases.
If this is not the case, then whatever you said after that, that will all change.
Which I said after that?
But I mean that if you...
Yeah, that will, because change means your H will get change. H I put a omega lambda, which is a constant, but that omega lambda has a, in fact, if you have a W, then your rho will scale as a to the power -3 into 1 plus W. So there in your extra parameter W, that will be there in H. Okay. So that is an extra parameter. So you feed that extra parameter now.
So the two Friedman equation that you write, A dot over A whole square equal to 8 by G, the two equations that you write, you said they are independent.
Now I said that in these three equations, any two are independent.
So A double dot over A, if we integrate that equation, can't we get that A dot over A equation?
As I said, so you can use these two to get this. I can use these two to get this, these two to get this. We can integrate, but in that case, integrating this is difficult, because in a sense that you get another constant of motion and all those things. But otherwise, these two comes from Einstein's equation. These two are purely G00 Einstein's equation and GII Einstein's equation. This is the energy conservation equation, but these are not independent because we have a Bianchi identity for the G nu mu semicolon nu equal to 0. The divergence of Einstein tensor is 0. So that's why means any two of these equations are independent. So I can use any two to get the other in principle.
Also, whether the energy conservation is the manifestation of the Bianchi identity of G nu mu?
In that sense, right. Actually, means Einstein put in the other way. Einstein put it that the T nu mu has to be conserved. That's why he didn't put R nu mu equal to T nu mu. He constructed R nu mu minus half R G nu mu, which is a divergenceless. So the way Einstein's equation was wrote at first by Einstein was that there is a energy momentum tensor which has to be conserved due to the defined conservation law. Then I have to put something in the curvature part which has to be also divergenceless. So that's why instead of R nu mu, we constructed a term called, that's why it is called Einstein tensor, which is R nu mu minus half R G nu mu, which is a divergenceless.
Sir, what was the other way you said we can find that equation?
Which equation?
So the one we were talking about,
This equation. So one is T nu mu semicolon nu equal to 0, that is the conservation. Another way is, then you can also use that your entropy is 0. So your du plus P dV, this is equal to 0, and this du is basically d rho a cube plus p d a cube. This is equal to 0, and this actually gives you this.
And in third equation, if you put rho equal to minus p, then you will get rho equal to the density parameter equal to constant, no?
And that I wrote.
Dark energy.
Dark energy, yeah.
Cosmological constant.
That I wrote.
Yeah.
Yeah, what you?
So when we say adiabatic expansion, that arises because of this conservation.
Yeah, because
Yeah.
Q is 0.
So why, from where did this thing come? Because
This.
actual, it is not necessary that this
Oh, why it is not necessary?
will be. Like in general relativity,
Mm-hmm.
how do we define energy conservation?
This is not energy, this is energy and momentum conservation. So it is give you the continuity equation and the Euler equation in general. No, you assume that, I mean, what you can assume that whatever the fluid or whatever the field or whatever you have, there is a certain energy conservation that you actually assume. So you assume that there is a energy conservation, and then you assume there is a momentum conservation. And that is encoded here. Okay. So if you write a field theory, so then your whatever you calculate the Noether charge or all those things, fine. That comes from your conservation of energy and momentum, fine. So in electrodynamics so this is, I mean, this is an assumption that you assume that your whatever fluids or whatever things you have, they actually satisfy the conservations, fine. And then you write the Gini mu. But now if you do the Einstein-Hilbert action, you write everything, then you don't have to assume it, I mean, like by hand, this comes automatically from your action variation, and you can get all those equations. No, it's not, means it's always true. P minus rho is basically the fact that you have homogeneous anisotropy. And then you take P minus rho, then you have this, that gives you this. But if it is not like that, if it is not like this equation, let's say in standard case, in Newtonian case, this will give you a continuity equation and the Euler equation, fine. The momentum conservation and the energy conservation. When you have any fluid or any field, you know its energy momentum, and then you write the energy momentum conservation, and you get different equation, whatever. I mean, like.
So they need adiabatic expansion.
That, and then means these two are consistent with each other.
One final thing we didn't do, but you can see from there is, so in the bottom half he gave you rho is proportional to a to the minus 3 or a to the minus 4. So now you can go to the top equation, that is just some function of a. So you can get a as a function of t.
A as a function of t. Yeah.
Because I will need the a as a function.
Yeah. So, okay. So I thought that means, okay. So if you put it there, and then you can get a as a function of t. Yeah. Means I skip that.